Hello everyone, welcome to the channel. In this video, I'll be introducing you to differentiation, and specifically differentiation from first principles, which would be the limit definition. So if you're completely new to differentiation and have no idea what it is, then this video will explain it from scratch. So the concept of differentiation consists of determining the gradient function of another given function. So no matter what starting function we have, at every single point, that function is going to have a certain gradient or slope. And now if this function is curved, whenever we speak of its gradient, we actually just mean the gradient of the tangent line at that given point on the function. Okay, so, but let's consider first the case of a function which is linear, a straight line. It's given by ax plus b, where a and b are parameters and x is the independent variable. So we know how to find the gradient of such a function. It's just the difference in y coordinates divided by the difference in x coordinates given 2 points on the function. So that would be y2 minus y1 divided by x2 minus x1. And we can rewrite this as f of x2 minus f of x1 divided by x2 minus x1, because y is just the function, okay? Now plugging in x2 inside the function gives us a times x2 plus b minus a times x1 minus b, because we have a minus in front of the brackets, so the plus turns into a minus. And then the b's cancel out, so in the end we can factor out an a from both terms after the b's cancel out. And in the brackets we have x2 minus x1, but we also have x2 minus x1 in the denominator. So that difference in x cancels out and we're left with just a. So what that tells us is that whenever we have a linear function of the form ax plus b, the gradient at any point on this line is always going to be a, which is just a coefficient of x. Okay, so it doesn't matter what point we pick, because since it's a straight line, the slope is always the same. It's just a constant. And if we have it in the form ax plus b, that slope is going to be given by whatever a is. So the concept of differentiation investigates how can we set up a function that tells us the gradient of a function at every single point, especially if we have a curved function, because if we have a curved function, the slope, the steepness is obviously changing. So the way we can go about this is by taking the same formula. The gradient is the difference in y divided by the difference in x, and this would actually approximate the curve to a straight line. But as the difference in x becomes very, very, very small, that straight line that we're approximating to is essentially going to be very close to the tangent of the curve at a specific point. So we will be using limits to let the change in x tend to 0. So we can just copy this f of x2 minus f of x1 divided by the difference in x. But let's say that the difference in x is now h, and we're letting h tend to 0, okay, just for simplicity. Now, f of x2 is going to be the same as f of x plus h, okay, given that x1 is just our x, because we want to have it to be a function of at a specific point. So we just say that x is going to be x1, and then how do we represent x2? Well, it's going to be that x plus a very small step, which we call h. So that's going to be the first term on our numerator. It's going to be f of x plus h, and then we're going to subtract f of x and divide by h, which is the difference in x. So this is just the exact same formula as before for a straight line, but we're just using h for the difference in x. And now we're going to use a limit and let h tend to 0. Because in the limit, as h is tending to 0, the straight line approximation that I was talking about essentially becomes the exact same as the tangent line to our function at that specific point. Okay? And we denote this new gradient function by f dashed of x, and this is also called the derivative of our original function f of x. So that is how we can set up this gradient function or this derivative function. It's with this formula, and we call this the limit definition of the derivative. And whenever we use it to determine the derivative function, we say that we are differentiating from first principles. And in this video, we will do a few examples in which we determine this derivative function for a few different starting functions. Okay, so the first function we're going to differentiate from first principles is f of x equals x cubed. And the first step is to just copy our limit definition, and then I'll substitute f of x plus h and f of x by our actual function, which is f of x equals x cubed. But for now, I'm just copying the formula. So when I substitute in for our function, we'd have the limit as h tends to 0 of x plus h cubed minus x cubed, all over h. And this is equal to the limit as h tends to 0 of x cubed plus 3x squared h plus 3xh squared minus plus h cubed, sorry, and then minus x cubed. So here I've just expanded the brackets. You have to know how to expand a cubic polynomial, and all this is divided by h. And we see how the x cubes cancel out. So we are just left with the limit as h tends to 0 of, now we can immediately divide all the terms by h. We're just left with 3x squared plus 3xh plus h squared. And now all of these, both of these terms which have an h in them just tend to 0 by direct substitution, which we couldn't do before because we'd have 0 in the denominator, and we're just left with 3x squared, which we can bring outside of the limit because it's not dependent on h. So 3x squared is our final answer. Next up we have f of x equals 5x squared. So again, I'm just copying the formula, the limit definition. That's always the first step, and yeah, so here I'm immediately gonna just substitute by our function. We have 5 times x plus h squared minus 5x squared all over h. And now I am going to factor out a 5 from both terms on the numerator. So I'm left with 5 times x plus h squared minus x squared in big brackets all over h. And now what I can actually do is just bring this 5 outside of the limit, okay, which I'll do in a second, because it's independent of h, it's just a constant. So I'm going to have just this constant 5 multiplied by everything else. The limit as h tends to 0 of this x plus h squared minus x squared, and then all over h. And now we realize that besides this 5, the other factor, which is the limit, all this is just the limit definition for the derivative of x squared, which in the previous video we established to be 2x, or in the first video rather. So in total we'd have 5 times 2x, which is 10x. Now this next function is with parameters, so we just have a constant times another function g of x, and that's our original function f of x. So we copy the limit definition. We're going to have the limit as h tends to 0 of k times g of x plus h, and then subtract k times g of x all over h. Okay, now we'll do a similar step as in the previous example. We are just going to factor out this constant k, and then we'll be left with, in big brackets, g of x plus h minus g of x over h. And in the next step, we will just bring this constant outside of the limit since it's independent of h. Okay, so once we bring the constant out, we'll just be left with the limit as h tends to 0 of g of x plus h minus g of x all over h. And hopefully you can recognize this to just be the limit definition for the derivative of g of x. So actually we're just going to substitute this whole limit by g dashed of x. And we've established a pretty important rule saying that a constant times a function g of x, when we try to differentiate this, we can actually just bring the constant out and say it's equal to the constant times g dashed of x, which is the derivative of g. Next up, we have f of x being a sum of two other functions, u of x and v of x. So again, we have the limit definition. H is tending to 0, and so we have f of x plus h minus f of x over h, and next we'll substitute f of x plus h using the definition for f of x. So that would be u of x plus h plus v of x plus h. And we still have to subtract u of x as well as v of x and divide everything by h. Okay, so this is the equal to the limit as h tends to 0 of now we can rearrange some terms. So this is u of x plus h minus u of x, and then plus v of x plus h minus v of x. So I'm not doing any calculations here, just rearranging the terms. It'll make the next step easier. And then all over h. So now we're actually going to use limit laws to split this limit into two separate limits in order to identify the two derivatives. You'll see what I mean in a moment. So I'm just copying it, but also I'm going to split the limit. So we did this, we covered this limit law in the very first video. So we're adding the limit as h tends to 0 of this expression with the u functions to this limit as h tends to 0 of this expression with the v functions. And now we must again recognize that the first limit is just the derivative of u as a function of x, and the second limit is just the derivative of v as a function of x, or u dash of x plus v dash of x. So that's it for today's video. And in the next one, we're probably going to cover some more differentiation techniques. We won't be using this limit definition every time, but we'll be using some common previously established rules so that we can differentiate more quickly. And we'll see how to do that in the next video. So make sure to watch that as well.